on. So basically, when we notice that there are some noticeable observations in terms of explosion inside the sample, so we find that typically we use 1 gram of the sample as given in the standard. So the experimental practice here did not really help us so much, even so we're using what's in the standard, but we noticed that 1 gram of the sample does not give complete combustion. So even so, we tested different crucible, different oxygen pressure, different pump sizes, ignition wires, and so on, in order to try to define why there is incomplete combustion. So basically, when we lowered the mass of the sample, we could obtain a complete combustion. So that tells us that actually the reason has something to do with how we perform, how the practice is. So in case of hard materials, like woody materials that are hard to burn, it is better to use a smaller masses. So, but it's still the question is, why not 1 gram? So the question is, why we can't burn 1 gram? Okay, we use a small one, so we obtain complete combustion, but the question is still, why not 1 gram? So when we consider the applied pressure to form the pellet, every user is basically making his own pellet. So that was one of the main reasons that some people were able to obtain a complete combustion and some people couldn't obtain a good complete combustion. So the pelletizer is actually a very important element in this process. So an over-pressurized pellet will develop segments and breaking points and eventually end up exploding inside the bomb. So this was one of the main observations that we saw. The second one here is the EMC. If you remember, I mentioned this earlier as one of the possible reasons of deviation. So the equilibrium moisture content is basically when the samples reach equilibrium with the surrounding atmosphere before determining the calorific value. So the standard gives you a possibility that you leave it just for 4 hours and you see how it goes. After that, you burn and see how it is after 4 hours. But obviously, this criteria could potentially is in most cases right, but not in every case is right. And this is a significant difference. And that's why when we tested in our lab conditions, we found that actually we reach equilibrium after 16 hours, and the repeatability of the samples are actually way better than when we follow typically the standards of leaving it for 4 hours and then we start determining the calorific value. So we could notice after longer time, less scattering with longer equilibrium time, significant repeatability improvement, but again, all this will eventually depend upon laboratory atmosphere, and that's why such observations have to be given to the operators in terms to consider such factors, in terms to realize such factors and avoid such mistakes. So a lab could stay for 4 hours and could have very good results depending on its conditions in terms of the temperature and humidity and so on. And another lab could potentially need more hours. So that leads us now to what actually the improved criteria. So the improved criteria that we recommended here is actually using a smaller mass, because we found that when you use actually smaller mass with materials that's hard to burn, you guarantee complete combustion. Even so, it will have an influence in the overall uncertainty, relatively increases the uncertainty, but assuring complete combustion here is a much more realistic approach than over testing with 1 gram of the samples and eventually getting a poor combustion. So the second factor was the applied pellet pressure, which is not mentioned in the standard. The standard leave it vague, and that's why when we found that within this range, you actually get relatively good coherent pellet, so that does not explode inside the bomb. So that we determine the uncertainty around 1% compared to 5% that is available in the market, 2 to 5% available in the market. But the standard itself does not give you the uncertainty budget. So also the ignition corrections when you flush with oxygen your bomb to replace the air, it will help lower the NO3 and SO4. Also, we consider such factors. These factors are not considered in the standard. Also, the RBM of the grinder, the EMC time, we propose 16, and the overall improvement is significant compared to the standard 50 to 80% in terms of repeatability, 15 to 30% in the final uncertainty. So this basically was the final conclusion from that experimental part. So that led us basically to the uncertainty. So now after we measured the values, so we did the results, we measured, and we had the finite calorific value. Now we need to determine the uncertainty. I mentioned earlier that we said it would be around 1%, but how did we obtain this 1%? First, we had to basically scan all the uncertainty sources and then analyze them one by one. So as you can see here for the energy content, for example, so we consider the sample mass one of the most important elements. You have the calibration process and the uncertainty associated to it, the temperature rise, delta T, which basically measured by a sensor. So we have to calibrate such sensor, for example. So basically all what is associated to the calorific value. So all elements we determined, and then basically, as I said, we did two different test cycles. So, but why it is important here, this is an example to show you how and why it is important. This was actually a previous call comparison that we participated, where we participated as PTB. So you can see here the different samples from different institutes, but you see how inconsistent the data is. So for example, someone, 1.3, for example, the same sample here is 0.02, while here, for example, 0.42. So the data is widely inconsistent. So again, you see such similar pattern in our cycle 1 according to the standard, because there is no methodology of how to determine the uncertainty at the first place. So that's why it is basically scattered. So you see again the data is scattered. Now when you see the final combined uncertainty of cycle 2, you see the data is relatively consistent. So you start to feel the deviation is actually much less. For example, this sample 0.38, the same sample in another lab 0.35, here in another lab 0.43. So the data are way closer. So that's why we can see that there is a significant improvement. And the combined uncertainty, so those are for each lab. But the combined uncertainty here refers to actually combining all the uncertainties from the other institute and put it as a one sum to give, we expanded, yes, the uncertainty more, but eventually we guaranteed that we managed all the data from all the three institutes. And by that, we actually concluded the uncertainty part. So all the previous parts have results in creating impact. So we published a paper in the journal, a comprehensive analysis of the risks associated with the determination of biofuels calorific value. So this has been published in Energies, and also we published, it's already published, also in chemical engineering transaction. This was a conference paper. This also has been published. So now that leads me to the future work. So now we know that this has a direct importance in terms of from a financial point of view. Now we wanted to validate this importance on an industrial scale. So biomass to SAF. It could be biomass to hydrogen, biomass to any other higher fuel. But here our work will be focused on biomass to SAF. So the objectives is basically will be discussed why we do that. But in order to do that, we have to just give a simple hint here. So We know that there are different factors of uncertainty sources in any industrial facilities. For example, the feedstock characteristics and heterogeneity, the process design dimensions and operating parameters, the supply chain of the feedstocks and the seasonal fluctuation, the instruments and the equipment, drafting controllers, and so on. So those are an example of the uncertainty sources available or typically does exist in a factory. So our work was directly related to the feedstock characteristics and heterogeneity. That's where our work is. So we, in 1.2, we were doing the energy content and participating in the moisture content, but we were not the only one. So our colleagues in the other work packages have been analyzing the CHNS, the ash composition, the impurities, and so on. So those represent the main properties that needed in order to design a process where biomass is used as a feedstock. So these here, for example, some of the examples of such results. So here, for example, some of the institutes working on that. So our future objectives is basically to do a literature review for the South pathway and specifying the most promising processes, sensitivity analysis to study the effect of biomass properties and the different types of biomass and its uncertainty on process design. So here in process design and the yield of obtaining SAF, techno-economic of the process, writing a journal and a conference paper. So yeah, this is our future objectives, and thank you very much.